So, Assalamualaikum warahmatullahi wabarakatuh. My name is Imran Hakim. So, today I will present to you about the abstract. So, the traveling salesman problem, TSP, is a well known mathematical problem classified as a non deterministic polynomial NP-hard problem, which tries to find the shortest route that passes through a set of points only once. The traveling salesman problem, TSP, has also found widespread application in several scientific and technological domains. It is very hard to solve effectively and efficiently due to its NP-hard nature. There are also a multitude of optimization approaches that have been proposed and developed by scientists and researchers during the last several decades. So for the nearest neighbor is a TSP heuristic method. The main objective of this algorithm is to visit the nearest city node. The time complexity of the nearest neighbor algorithm is O(n)2. Based on the previous research, the Helga algorithm is used to optimize the delivery route, considering efficient distance and delivery sequence. Helga algorithm produces better results than the iterative deepening search algorithm in finding optimal delivery routes. This study proposed a base case to determine NNA for solving the symmetric TSP. Traveling salesman problem TSP finds the shortest Hamiltonian cycle in a graph, and it is improved NNA where it starts with the shortest edge consisting of two cities. Then it includes the closest city on the road repeatedly until an effective route is established. So for the introduction, the traveling salesman TSP problem the traveling salesman problem TSP involves finding the shortest possible route that visits a set of cities exactly once and returns to the origin city. This problem is NP-hard and has numerous real-world applications in logistics, robotics, and delivery systems. Due to its computational complexity, it is essential to evaluate both exact and heuristic approaches. TSP is used to find the shortest Hamiltonian cycle in a graph, with exponentially increasing in complexity to solve large problems with guaranteed optimality. There are also several algorithms used to find optimal tools, but none lead to feasible mountains solutions for large instances since they all grow exponentially. The nearest neighbor is a TSP heuristic method where the algorithm is to visit the nearest city node. The time complexity of the nearest neighbor is O(n)2. The helicopter algorithm is used to optimize the delivery route considering efficient distance delivery sequence. Helicopter algorithm produce better results than the iterative deepening search algorithm in finding optimal delivery routes. So the problem statement. The traveling salesman problem TSP represents a significant computational challenge in the field of combinatorial optimization due to its NP-hard nature. As the number of cities increases, the complexity of finding an exact optimal solution grows exponentially, making brute force and exhaustive search methods impractical for real-world applications. Heuristic algorithms, like the nearest neighbor algorithm, offer a faster and more scalable alternative, but often sacrifice accuracy due to their greedy and locally optimal decision-making process. The quality of the solution from NNA can vary significantly depending on the starting point and may not reflect the globally shortest path. So, in for the next problem statement, in logistics and transportation, it determine the most efficient route that minimize distance and travel time is essential for reducing operational costs and improving delivery performance. While exact algorithms such as Helicop and provide optimal solutions, they become computationally expensive and infeasible for larger datasets. This study addresses the challenge of solving the symmetric TSP using a baseline heuristic approach, the nearest neighbor algorithm, and evaluates its performance on a dataset of Malaysian cities. And also for the kuliah IUM, this goal is to assess the effectiveness of the heuristic in producing an efficient travel route and compare its practicality against the theoretical optimal methods in terms of distance, travel time, and computational efficiency. For the research objective, our primarily research objectives are: first one, implement the nearest neighbor algorithm NNA as a heuristic method for solving the symmetric traveling salesman problem (TSP) using a real-world data set of selected Malaysian cities. Second, determine an efficient travel route that minimizes the total travel distance and time between cities based on a given distance matrix. Number three, evaluate the performance of the NNA in terms of total distance, time travel, and computational speed, and identify its strengths and limitations when compared to optimal solutions, such as the Helka algorithm. Number four, analyze the practical applicability of heuristic methods like NNA in the real-world logistics and road optimization scenarios where computational efficiency is crucial. Number five, provide visualization and interpretation of the computed travel path to support data-driven decision-making in transportation and planning tasks.
Assalamu alaikum. My name is Yusuf, metric number 2314467, and I will be going through the data sets. So, in this project, we have two data sets. In this slide, you can see the data set of Malaysian countries. So we chose 10 major cities: KL, Penang, Johor, Ipoh, Malacca, Kuantan, Kota Baru, Kuala Terengganu, Alasutra, and Serembang. And we found the distance between each cities. As for the time taken to travel to these cities, and we sorted them into matrix, as you can see here, and then in a table. So the distance is in kilometers, and the time taken is in hours. So as for the second data set, we found the distance between each kulia in IUM Gombak. So there are total 8 kulias here. Kulia of law, ICT, econs, education, engineering, architecture, IKHS, and CELPAD. And we calculated the approximate distance in kilometers here, as well as the time taken to travel by foot from one kulia to another kulia. And these two are the table, matrix table you can find. So the highest it takes is to go from KICD to iCall is KICD to Kenmas is 31 minutes, and the fastest is between CellPad to KIKHS is just 1 minute. So the methodology we use to calculate the distance between these cities and Kulia is called Euclidean distance formula matrix. And what we did is we found the distance between each of the cities, and we straight it down in a matrix one by one from one Kulia to another Kulia, from one city to another city. And as you can see, this is good enough because we've calculated large distance as well as small distance, so that we can find out in the end if large and small distance matter in this report, in this research. So before we started the report, we found the dataset, and now we had to find the algorithm. So for TSP, traveling salesman problem, we have five main algorithms. So it is brute force, Helka, nearest neighbor, genetic algorithm, and simulated annealing. Out of these five, only two of them were found to be competitive and the best. because genetic algorithm and simulated annealing are both heuristic approach, but the complexity varies when the distance or the number of dataset um, increases or decreases. So we can't really compare these two. Aside from that, brute force is not supposed to be a competition between Hellcarp and AS Neighbor, because brute force is an approach which we can use in all of the algorithms. So what we found is Hellcarp and AS Neighbor, and Hellcarp's complexity is O and it's n square into 2 raised to n. As for nearest neighbor is O n raised to n square. So these two are highly competitive, and let's find out how they give the result to these two data sets we have. So the first algorithm we have here is called Hellcarp algorithm, and it's dynamic programming. So Hellcarp is a classic exact algorithm. Uh, Unlike brute force, Hellcarp reduces computational complexity to O n square into 2 raised to n, which is really fast and efficient for higher size data, for higher sized data sets. So if you're comparing this with a brute force algorithm, Hellcarp vs brute force algorithm, the key advantages are the efficiency, because Hellcarp is has less computational time, and it guarantees finding the shortest possible route. Unlike brute force you can find a route, but it might not be the shortest possible route. And finally, scalability. Um, Brute force is works perfectly when cities are less, like 20 to 25 cities when the data set is less, and it is useful for logistic problem solving with higher accuracy. So as you can see before that, Hellcarp is better than brute force, and why is that? Because of the time complexity is better as for the space complexity as well, and when the input size is higher, it's better than the brute force, and it's also faster due to memorization compared to brute force, because it's slow, because it's exponential. As for the second algorithm we used is called nearest neighbor, and it's a heuristic approach. So nearest neighbor is one of the simplest and the fastest method for solving traveling salesman problem. It does not really guarantee an optimal solution, but it provides a quick approximation. So it's good for large dataset where methods became infeasible. So how does this work? So um, the algorithm works by starting by choosing a city first, and then each step it will find the smallest distance, and for the next city. So it repeats this step until the last city, all the three cities are visited, and it returns to the starting city. For example, if you take the example of nearest neighbor, how it works, it starts with the city. For example, we're starting with city A. So let's find the least its distance. The least is 10, which is in B. So you go to the B row and you find the least distance between B, and the next least distance is E. So the E is 17, and it goes back to E's row. And in E's row, you can find the distance, least distance is 16 from E to D, and it moves to D's row. And as you can see, D to C is the smallest 30. So once you calculate all the distance, the total cost is 73. This might not be the optimal distance, but it should work, and it should provide the least distance. So to compare them both, Hellcarp and nearest neighbor, the time complexity for both is almost similar because it's multiplied by 2 raised to n. For the space complexity is more in Hellcarp algorithm, and less in nearest neighbor. But Hellcarp is more optimal because it provides the best route, but it takes more time. As for the nearest neighbor, it's good for large data set because it's really fast, but it might not provide the best route, but it should provide close enough to the best route. So Algorithm is always the perfect one, the best, and but nearest neighbor, it could be optimal. Depends on the data set size. Helcap is complex, as nearest neighbor is very simple. That's why it's fast. So near, for nearest neighbor, they have the starting point sensitivity because nearest neighbor starts with 1 point. But for an exact algorithm for Helcap, it can start from any point and it can find you the best optimal route.
Alright, so now we move on to the discussion part. The first algorithm, which is the Helk algorithm, is an exact algorithm used to solve the traveling salesman problem with a time complexity of O n squared times with 2 to the power of n, where n is the numbers of places. This method guarantees finding the optimal, shortest possible route, but its computational cost grows exponentially with the number of nodes. So how this works is, first it uses bit masking to represent subsets of places. The dictionary C stores the minimum cost to reach a subset of places ending at place K. It iteratively builds solution for subsets of increasing sizes until the complete set is covered. After considering all possible subset and paths, it finds the minimum path that visits all places and returns to the starting place. And the last one is the path is reconstructed in reverse by tracking the parent place that led to each place. Okay, now so we move on to the second algorithm, which is the nearest neighbor algorithm, which is a greedy heuristic for TSP with a time complexity of O n squared. It does not guarantee an optimal solution, but offers a fast and reasonably good approximation, especially useful for large data sets. So how this works is, first start at an initial place and not zero. At each step, move to the closest unvisited place, and then continue this process until all places are visited. And the last one is optionally return to the starting place to form a complete cycle, depending the return to start flag. But for this case, we don't use that. Alright, so now we move to the result and analysis. So as you can see here, this is the distance matrix. The first one is the distance matrix pairwise road distance in kilometer between all 10 major cities in Malaysia. And then the second picture is the distance matrix pairwise road distance in kilometer between all 8 kuliah in IIM. Alright, so now to the next page. So this one is the total distance on how many kilometers that the algorithm decided for Malaysia cities and also for the kuliah buildings in IIM Gombak. So for the Malaysia cities, for the Helka algorithm is 1875 km, and for the nearest neighbor algorithm is 1690 km. And then for the second data set, which is the kuliah buildings in IIM Gombak, is for Helka algorithm 2.91 km, and then the nearest neighbor algorithm is 1.81 km. Okay, so now we move to the last part for result and analysis. For the first one is computation time and comparison. So for the Helka algorithm using dataset Malaysia cities, the computation time is 0.0045 seconds, while the other three, which is the nearest neighbor for Malaysia cities, the Helka algorithm for IIM kuliah buildings, and nearest neighbor using IIM kuliah buildings dataset is 0.00 seconds. Now we move to the total travel time for the Helka algorithm. For the first dataset, which is the Malaysia cities, is 21 hours, while for the IIM kuliah buildings is 29 minutes from ICOL to KA. And then for the nearest neighbor algorithm, using Malaysia cities dataset, is 21.3 hours, while the travel time between kuliah is from ICOL to KIST is 26 minutes. Alright, so now we move to the analysis summary. So for the Helka algorithm, it produced the shortest possible route, optimal, for both datasets but requires slightly more computation time, which is the 0.0045 seconds for the Malaysia cities dataset. The nearest neighbor algorithm produces a route faster, which is a zero computation time noticeable for small datasets, but the total distance and travel time were slightly higher compared to HELCAP algorithm. For the IAM Kuliah dataset, both algorithms show negligible computation time, but HELCAP again provided a better total distance and travel time. This confirms that HELCAP is suitable for small size problems where optimality is required, whereas nearest neighbor is suitable for faster approximate solution with larger datasets.
So how does these algorithm works in different places and in different applications? So in this section, we'll go through 5 different applications of this algorithm, and we'll find the best and the worst algorithms to use for this applications. So in logistic and supply chain, it is recommended to use hybrid strategy because HELCAP is used for small routes, but nearest neighbor is used for large. So it depends on how large is the supply chain. So it's better to use hybrid strategy because each route optimization might save thousands in annual saving. As for the robotics and autonomous system, I think it's better to use. It depends on the environment, which algorithm to use. So HELCAP is used in static environment for battery optimization. As for nearest neighbor, it's used for dynamic obstacle where they have multiple robots coordinating. If just one or two robots and it's in static, then it's better to use HELCAP. Where it's multiple robots and there's many chain of rules, then you have to use nearest neighbor. As for delivery route planning, it's better to use both as well because the longer the distance and the number of places to deliver to, it's better to use nearest neighbor. But if you are using the same delivery and the fastest route to go there, it's better to use HELCAP. As for the campus and urban navigation, it's better to use Helka for small campuses like small like under the mahalla and stuff. But if you wanna go for large university like from Kulia to Kulia and different mahallas and stuff, then it's better to use nearest neighbor because it's a large data set. So it depends on the area and this is schedule flexible. As for the manufacturing and production, the last one, if you want precision work, like exact work, then it's better to use HELCAP. But if you want warehouse picking and high volume operations, like which has multiple options, then it's better to use nearest neighbor. So it depends on accuracy or processing time. So to conclude, this project or this report was to find the distance and to find the two algorithms and to compare their functionality, optimality, and the speed as for the computational time between the two datasets provided. So the output, we can say that the HELCAP is the best, and because it finds the best possible route, but it takes longer time, especially when the dataset is larger, when there's more cities. But nearest neighbor finds a good route quickly, but they might not be the absolute shortest route. So there is ups and downs for both HELCAP and nearest neighbor, but HELCAP only finds the best possible route. So how to choose this? It depends on how big is the dataset. So if you want to get the shortest possible route in the shortest time, is better to use the nearest neighbor. But if you are using it to save costs and stuff, then it's better to use the HELCAP method because it takes longer time and it finds the best possible route. So although we tested for small cities like only 10 cities and only 8 kulias, you might find it more in future. But it really works in real life situations. And this research might help few people in future for choosing and planning routes that can guide future studies with larger data set. So this is it from group 404. Um, Inshallah, I hope you like this project and report. If we have missed anything, feel free to contact us. And thank you for going through this presentation and this report. Assalamu alaikum. Jazakallah khair. Taqabbalallah minkum.